Hello, my name is Richard Liu, and I'm pleased to be presenting our CVPR 2026 highlight paper, Deep Feature Deformation Weights. Let's start with some background. We're interested in the task of handle-based mesh deformation, which is traditionally approached through a linear blend skinning framework, where each vertex receives some deformation, which is a linear combination of deformations assigned to K handles. This formulation is popular because the final deformation is extremely fast to compute, but still allows fine-grained deformation control through the control handles. In this equation, Vi and V'I indicate the starting and deformed positions for vertex I, respectively. dk is the affine transformation assigned to handle K, and W is the weights matrix, where the IK entry stores the blending weight between handle K and vertex I. V is of course given by the input mesh, and dk is given by the user. Classical methods will then typically solve for W through some energy minimization problem. Importantly, the optimization problem is solved for a specific set of K handles. What this means is that handle set updates always require re-solving the optimization problem, which is expensive and scales poorly with mesh resolution. Furthermore, the energies are usually distortion-based, which means the optimization aims to minimize surface stretching and constrains each handle to have local influence over the surface. So minimizing the distortion energy is great for when you want to preserve the overall shape volume, but prevents potentially desirable shape edits, such as symmetrically stretching the blades of this axe model. Importantly, classical methods have no ability to understand shape-part relationships, and thus cannot preserve important shape semantics. More recent data-driven methods have since emerged to address that limitation. Specifically, these methods allow for surface distorting edits while aiming to preserve important visual attributes and part relationships that constitute the shape's identity. On the flip side, these methods also come with their own strong limitations, namely that they are slow and often require expensive pre-training on large datasets or optimization. Furthermore, there is no fine-grained control over the edits they produce. Users cannot assign specific transformations to handles for these methods in the same way they can for classical methods. So our goal in this work is to marry the advantages of both methods, the speed and control from classical linear blending, and the shape-aware priors from data. And our simple insight to achieving this is to use foundation model features to define the blending weights matrix in the linear blending equation. Let's go over some specifics. Given an input mesh, we first render multiple views and obtain image features for each view. We then take those encoded renders and distill the image features into a neural field using a novel distillation technique we call barycentric feature distillation. More on this in a second. So given the optimized neural field phi, we can then define our deep feature deformation weights with the following formula, which is simply the L2 distance between the features queried at vertex I and handle K. Note that in order to avoid negative weights, we unit normalize all features before distilling them into the neural field. Let's dive into the specifics of barycentric feature distillation. Assigning image features to 3D shapes is nothing new, and past works have typically mapped these features to vertices of the mesh. Given a single rasterized triangle then, you can expect only one pixel in the render to contribute a feature to each vertex, which is highly inefficient. Our proposal is to instead map features to points in 3D space, which means every pixel which is covered by a triangle becomes a useful signal. In fact, this approach ensures every mesh render is utilized to its greatest efficiency, as every pixel which contains a shaped surface will be utilized in the distillation process. An extremely valuable consequence of this approach is that we effectively disentangle distillation complexity from mesh complexity. Instead of the ground truth data and number of optimization variables being determined by the mesh vertices, which often represents a highly irregular and uneven sampling of the underlying surface, the ground truth samples are now determined by the render resolution. And since render resolution directly corresponds to visual detail, this aligns perfectly with how image feature quality scales with render resolution. So practically speaking, this makes barycentric feature distillation highly robust to mesh resolution. We can consistently distill shapes with tens of millions of elements in under 2 minutes, whereas previous methods would take hours to days, or more likely simply hit memory limits and fail.
To empirically quantify this speedup, we perform an extensive timing comparison across classical and data-driven baselines. We split the deformation pipeline into 3 commonly shared phases and remesh the approximately 6,000 shapes in our evaluation datasets from 1,000 to 10 million triangles. The pre-process phase contains our feature distillation time, which, as expected, is nearly constant with respect to mesh resolution. Furthermore, our method is faster than or is on par with all baselines across all resolutions.
Our neural field representation not only supports our distillation technique, but also enables a novel symmetry detection approach. Suppose we wish to evaluate a possible symmetry plane down the vertical axis of this human model. Though geometrically it is clear there is no symmetry, visually and semantically we understand the shape is symmetrical. The relevant parts are simply in different poses. Our symmetry detection procedure detects these types of visual symmetries. We look at the features on one side of the candidate plane, then reflect the queries across the plane and compare it to the features at those reflected queries. And we do the same for the other side of the shape. Note that these reflected queries do not exist on the original shape. The only reason we are able to obtain meaningful features for these queries is thanks to the neural field representation, which smoothly interpolates features throughout the entire 3D ambient space. With our symmetry plane active, we are able to perform complex symmetric deformations, which would be impossible to achieve without having correctly identified this symmetry. We also note this concept of visual symmetry is related to intrinsic symmetries, which was investigated by Max Ovsyannikov et al. In 2008. Though we know intrinsic symmetry detection is still sensitive to local geometric differences, such as the differing folds of the cloth geometry, whereas our detection is robust to those low-level geometric differences. Let's see some results. DFD weights allow for both complex affine transformations as well as single-handle feature stretching. DFD weights can also be made to have more or less local influence using our geodesics-based locality weighting scheme. We also offer a feature-based analogy to the fixed point constraints from classical methods, where our fixed points correspond to constraints of the feature space itself. Specifically, fixed points under our framework will constrain all other points which have similar deep features to those fixed points. And finally, we have code and an interactive GUI with all the aforementioned features implemented and available online. For more details, please check out our project page and paper, and thank you for your time.